So in this video, we're going to do some two-step problems converting from particles all the way to mass or from mass all the way to particles. So either way, if we go to particles to mass, we have to first go to moles and then go to mass. And if we go to from mass to particles, we have to first go to moles and then go to particles. So we're combining our two formulas that we learned in the previous videos. Let's go ahead and try some of those two-step problems. We'll put a reminder of what our basic formulas are. So mass is equal to the number of moles times the molar mass. And then also the number of particles is equal to the number of moles times the Avogadro's number. And I'm just going to put what Avogadro's number is equal to here. So remember that the Na is equal to 6.02 times 10 to the power of 23 particles per mole. Particles per 1 mole. So that's a good reminder. So let's start with our first question, question number 5. We want the mass of 2.3 times 10 to the power of 24 atoms of silver. So what are we asking you for here? Now, usually I use the guess method, but I want to try to walk you through this logically to question you as we do this so you understand what's going on. Yes, those methods are good to help keep you organized and everything, but you can keep yourself organized in a logical fashion without using guess. So we are looking for, let's write this out here. We are looking for, what's our unknown? We're looking for the mass. And so we know for the mass that you need to do your number of moles times your molar mass. And what do we have from here? Well, let's take a look. So we need number of moles and M. So what we do have is the molar mass for sure. We have the molar mass of silver because that's the element in question. And that's from our periodic table. But we need to have the number of moles. Okay? So this is sort of my planning process here. And so I'm going to write down next what I need to do is I have my molar mass of silver. If you go look at your periodic table, the molar mass of silver is Ag. So Ag is over here 107.87. 107.87. Okay. But I need to find N using my formula up here. I have the number of atoms. I can find my moles using the formula N is equal to big N over Na. And so I'll do that. Because to do really this whole problem, I need number of moles and molar mass of Ag. I have the molar mass of Ag. So I'm going to go and find the number of moles of Ag so I can plug it into that mass formula, which is really what I want to do. So I want to use that formula. I have the molar mass. I need to find the number of moles. I have the number of particles, and I can find the number of moles using the number of particles. So that'll be my step 4 here. I'm just going to continue up here. Step 4, my number of moles is equal to the number of particles, which is 2.3 times 10 to the power of 24 Ag atoms divided by 6.02 times 10 to the power of 23 Ag atoms per mole. And so I can cross out Ag atoms, mole is line over line, so it comes up. And I get, so 2.3 times 10 to the power of 24 divided by 6.02 times 10 to the power of 23. And I get this. I'm not going to round yet. I only round at the end. I get that N is equal to 3.82059807. So 3.820598.007. And that's moles. And so now my step 5 is I can go plug all that in. I can go back. I now have my N over here. I have my molar mass of Ag over here. I can go in my step 5 and do that and plug all that in. So I'm out of room here, so you want to make sure you have room. But for step 5, I'm going to do it right here. Mass is equal to the number of moles that I found. I'm not going to write all the figures down, but you should have them in your calculator. Okay, so I'm keeping all these figures in my calculator. 3.82 moles times the molar mass, which was 107.87 grams per mole. That's grams per mole. You can cancel out moles, and you end up with that the mass is equal to, so times 107.87, and we get 412.127 grams. And then you can just say it, therefore, the mass is approximately, we need to round the 2 sig figs. So if we're rounding the 2 sig figs, we need to round basically up at this point over here. So we look next door here, we're rounding down 410 grams. So this was very similar to other problems. It's just that we were missing a variable. So we had the molar mass to calculate here, but we didn't have the moles. So rather than directly tell you moles, we decided to make it a bit more difficult on you. We said, well, here's the number of atoms you have. Use that to find moles first, and then come back and use the mass formula. So to do that, we had to make a connection. We had to make a link. We had to use another equation, which was this equation over here, which came from, so let's call this equation 1. This is equation 2. So we had to use another equation to find the number of moles. Then I could go back and plug it into the equation I wanted to use. So let's go ahead and try another one. Let's use a different color here. Let's go with green. So how many formula units are in 300 grams of iron 3 chloride? How many atoms are there? So there's 2 questions there that we have to do. 2 questions. We want to find the number of particles of iron 3 chloride and then the total number of atoms in there. So I'll call this part A, and I'll call this part B. Let's do part A. We want to find the number of particles. So we want to find that by doing N is equal to the number of moles times the Avogadro's number. Okay. Now, the problem is, so we do have Avogadro's number, but we don't have the number of moles. So we need N and Na, and we have Na. So I'm just going to say, see that above. I'm not going to rewrite it here, but you can see it over here. But we need to find N using this lovely equation here. N is equal to the mass over the molar mass, right? That comes from equation number 2 over here. And so we can put N is equal to our mass, which is 300.0 grams, over the molar mass of iron 3 chloride. So that's FeCl3. Remember to do your crisscross. So let's just put a note here. That's FeCl3. If we did the molar mass of iron 3 chloride, so chlorine is 35.45 times 3 plus iron. Let's go see iron. So chlorine, let's just make sure 35.45, 55.85. There's only one of them. That's going to be over 162.2. So 162.2 grams per mole. Cross grams out, mole remains. And so we get 300 divided by that answer. And that will give us that the number of moles is 1.8495 and then 68434. moles. So now that I have the number of moles, I can go to step 4, which is go back to my formula that I had to begin with and plug everything in because I have everything I need. So I'm going to do my number of formula units is equal to, and I'm not going to write all this down. I'm just, keep in mind, it's all my calculator, but I'm just, to save space, I'm going to put 1.849, I'll stop there for now, moles times 6.02 times 10 to the power of 23 FeCl3 formula units. So I'm going to put, for formula units, I'm going to call it F.U, formula units per mole. And so I can cross mole out and cross mole out. And I'll be left with the correct number of formula units, hopefully. So let's do times Avogadro's number, 6.02, times 10 to the power of 23. And I get 1.113440197 times 10 to the power of 24 formula units. And then you could put your therefore statement. So therefore, n is equal to approximately, we want to do 4 sig figs. So 1.113 times 10 to the power of 24 FeCl3 formula units. And so that was for part A. How many formula units of the iron 3 chloride are there? And we found that there. But then we have a part B. So we have a part B as well. So let's make part B in this blue color here. How many atoms are there total? So for part B, my first step is going to be to make a conversion factor. So in one FeCl3 formula unit, how many atoms are there in total? Well, there's 1 iron and 4 chlorines. So that's going to be, and 3 chlorines, so that's going to be 4. 4 atoms total in one. So that's my conversion factor. So really, I just need the number of formula units that I already have, and I can multiply this by the conversion factor. So I'm taking my number of formula units that I have here, and then I'm multiplying it by the conversion factor. It's kind of like saying, if you had 1 FeCl3, how many atoms are there? Well, there's 4. If you had 2, well, you do 2 times 4, that's 8. Here we have 1.113 times 10 to the power of 24. So I'm doing that times 4, and that'll give me my answer. But let's see why that works. So we're going to do our multiplication. So we take our 1.113. I'm leaving the whole thing in my calculator. I'm not using the rounded answer. I'm going to round again at the end. So I don't want to round too many times here. So I'm going to write it down the way I had it rounded here, but in reality, I'm using my non-rounded answer. So times 10 to the power of 24 FeCl3 formula units. Multiply that by 4 atoms for every 1 FeCl3 formula unit, because that allows me to cancel these out. And I'm left with atoms. And so I do that times 4. I get 4.453760789 times 10 to the power of 24 atoms. And then I can say, therefore, the number of atoms total is equal to, we want to do this to 4 sig figs. So 4.454, because 3 rounds up to 4 there, times 10 to the power of 24 atoms. And that is my final answer for that particular question. So notice that we had to find the number of formula units first from the mass. So to find that from the mass, you had to go to the moles first by multiplying by molar mass. Then it went from moles to, sorry, by dividing by molar mass, right over here. Then it went from moles to the number of formula units by multiplying by the Avogadro's number. And that gave us our number of particles. Then to find the number of atoms total, we just had to multiply by the number of atoms in one of them, and that was to multiply it by 4. And that gave us our final answer there. So we're going to do question 7 in this video, and then in the next video we're going to do questions 8 and 9. So let's do question 7. Again, you can pause this yourself and try it yourself. There's not a lot of room here, so I might go to a different document and continue the question there. But it's the same essential format that you're going to follow that I did for the previous question. So how many hydrogen atoms are there in 68 grams of H2S? So we're looking not for just the number of particles. We're looking for the number of hydrogen atoms in total within that number of particles. So if I want to find the number of hydrogen atoms, here's what I need to do. I need to do the total number of particles of H2S. And I need to multiply that by, well, 2 hydrogen atoms per H2S. Right, that's my conversion factor, because then I can cross out H2S. The problem is I don't have the number of particles yet. So let's go ahead and do the number of particles, find the number of particles. I'm going to use conversion factors only right now. So my first step from here is to get to moles. So I have 68 grams, and I'm going to multiply that by my molar mass conversion factor. The molar mass of H2S is, so 2.02 plus 32.04, 34.06. Let me just make sure that's right, because I think we calculated that earlier. I thought we did. Yes, we did. So it was, 34. H2S, 34.09 rather, sorry, 34.09. Okay, so grams per mole. So I need to find moles, so I need to have grams at the bottom for 1 mole. This is my molar mass conversion factor. So 1 mole over 34.09. So I can cross out grams and grams. So at this point, I'll be at moles. And then I'm going to multiply by my other conversion factor, which is the to get from moles to particles. So 1 mole over Avogadro's number, which is Avogadro's number over 1 mole, 6.02 times 10 to the power of 23 H2S molecules. And so that's going to cross out moles and moles, and I'm going to be left with molecules. And then finally, I can multiply by my last bit, so I'm going to continue this here. So I'm just going to put this in my calculator right now. So I'm going to have 68 times 1, well, we're dividing here, so 68 divided by 34.09 times 6.02 times 10 to the power of 23. And so I'm just continuing this process here. I get 1.2, and I'm not going to write everything down, but I'm going to write as much as I can down here, times 10 to the power of 24 H2S molecules times a conversion factor of 2H atoms per H2S molecule. And so I can cross out the H2S molecules there. And I get atoms left over. And so I get 2.4016 times 10 to the power of 24 H atoms. You can then write a therefore statement to the correct number of significant figures, which is 2. So I'm just going to do that over here. So let's just do that over here. I recommend you do this on a piece of paper so you have more room. Therefore, the number of H atoms is equal to 2.4 times 10 to the power of 24. I'm just going to put H atoms. And that there is my final answer. You'll notice that I did only conversion factors here. You could have used all your formulas, or you could have just set it up with conversion factors to attempt that. So whatever you're more comfortable with, conversion factors is a bit quicker, especially if you get the hang of it. So in the next video, we're going to do questions 8 and 9.